Welcome to Homework Lib.
So part A of this problem asks for the energy of a photon emitted from the 3D to the 2p state. So we know the formula E equals hc over lambda, where h is Planck's constant given in electron volt seconds. Lambda is the wavelength given in the problem, and c is the speed of light. And if you plug in those values, you get 2.612 electron volts. And then part B of the problem is asking us to use selection rules described in section 41.4 to find the allowed transitions. So based on the selection rules, we know that delta L is 1, and correspondingly delta ML can be basically negative L, 0 to positive L, so 0 plus or minus 1. So if we write out all the states if we write out the quantum numbers for 3D, states 3D and 2p for 3D, n equals 3, L equals 2, and ML is plus or minus 2 plus or minus 1 and 0 for 2p, n equals 2, L equals 1, and then ML is 0 and plus or minus 1. And so listed on the left here are all the possible combinations where L is equal to 2 and ML is equal to 2, 1, 0, negative 1, or negative 2. And so we want the transition to go where L jumps down 1, or ML does not jump down at all, or goes plus or minus 1. So listed are just all the combinations where L goes, where L prime minus L is 1, so that's 2 for L and 1 for L prime, and where ML is 0, 1 or negative 1, so that's, for example, in the first column, first row, it's ML starts off as 2 and then goes to 1, or you can also, down here, ML starts at 0 and then goes to negative 1. Part C of this problem is asking for the energies of the states into which it splits. And so we know that delta E equals mu B times the magnetic field. Mu B is again a constant given by 5.788 times 10 to the negative fifth electron volts per Tesla, and the problem says B is 3.5 Teslas. So calculate delta E to get 2.03 times 10 to the negative fourth electron volts, and therefore the energy is negative 8.5 electron volts, which is given in the problem, plus or minus the 2.03 times 10 to the negative fourth electron volts. The last part of the problem is asking for the allowed wavelengths during the transition given in part B. So from part B, we know that the energy was 2.612 volts. From part C, we know that delta E is 2.03 times 10 to the negative fourth electron volts. And from the same formula we used in part A, which was this formula, if we rearrange it, we get lambda equals hc over delta E. And then plugging in the same constants, Planck's constants, the speed of light, and the two delta ET values that we get from this equation up here, you get that lambda is 475.04 nanometers or 475.12 nanometers.